Thank you, Jenny, and welcome everyone to an excellent panel on characterizing local scale pollution sources. I'm really excited for the presentations today and for the Q&A afterwards. So without further ado, I'd like to introduce our first speaker, who is Ted Russell from Georgia Tech.
So yeah, what I'm going to talk about is address some of the questions and issues characterizing local scale air pollution. And this is going to highlight some of the work that we've done at Georgia Tech with my colleagues, Jen Kaiser, Talat Odman, Young Tao Hu, and the student who's now working on it, Ariana Moore. And we've done this in collaboration with CDC and others, but it's going to go beyond just our work, as you're going to see. So basically, I think we've heard this quite a bit in the HAQAST presentations already, is that there's a keen interest by scientists as well as most of the stakeholders in looking at how to accurately characterize the impact of local sources on exposures. And this often involves addressing and estimating source strengths, which are viewed as relatively uncertain, and actually even sometimes source locations, etc. And in particular, some of these local sources, and really how we got involved in sort of going the direction we did looking at ports, was that they can lead to environmental justice concerns. They're often, these are located in communities, lower income, various ethnicities and backgrounds. So, things like rail yards, shipping ports, airports, etc. And one thing that often comes through, and the real power, one of the reasons we really look to having satellite observations, is that in situ observations from fixed site observations or even mobile platforms, they're limited both spatially as well as either spatially or temporally or both. And so they just don't provide the information you need. So the satellites are really providing this type of information, and they're increasing in spatial detail. And so that's why we're so excited about using them. And in particular, we're looking at advances primarily in the PM and NO2 retrievals, given their direct impact on health effects, but even more so, at least from my end, is how they can tie to other pollutants as well. And we look to the future as being even more exciting. So just as an example, what I want to bring up is some of the work we did in the Atlanta area. Georgia Tech is actually, if you can see the arrow right up, we're right about there. And looking forward to what Byeong might say next, is this is actually driven by a conversation I had with another member from the Georgia DNR, Jim Boylan. Just looking at some of the recent tropomi retrievals, looking at the NO2 vertical column densities, you look at this picture, and what you could see is that, and this is Atlanta, and these black lines are the major freeways running around Atlanta, and right through the middle of Atlanta is something called the connector, where multiple freeways come together. These are have the highest traffic densities in the region, and in fact, some of the highest in the southeast. But what you actually see is that what gets highlighted when you look at the NO2 columns were the two power plants and, in essence, the airport, really highlighting the impact of the airport on NO2 in the area. And so what these retrievals do, it not only helps us to characterize the impact of these NOx sources, but even show in a relative sense just their importance, even without looking at characterizing the sources just in detail. You can just use these to help identify these are sources of importance. And there's relatively few NOx monitors that can really capture the details and the spatial extent of the impact of these various NOx sources. So that really shows the power of these capabilities in terms of identifying and helping to characterize the sources. Now, what you can do is actually, and what we've done is magnify the power of just the satellite data by integrating it with air quality modeling. And we've done this both using CMAQ as well as some dispersion modeling. But just to highlight sort of what we've done with CMAQ is we can compare the columns that are observed with those that we simulate. And this is the graph you get. This is the Tropomi NO2 versus the CMAQ. And you see that the two actually compare well. You do see this bias, and we're working on this bias. We think we have some reasons for looking at it. But the other thing it allows us to do, and I think it'll allow even more detail in time, and you've seen other people use this sort of information. I think it was Davin looking, or Randall looking to use this type of information to improve NO2 or NOx emission inventories. And then once you do that, just as others have shown, you can use the air quality model to assess the impacts on other pollutants. So it's not only the work we've done, this is something that was highlighted yesterday as well, done by investigators at NASA's, and they contacted some of us working with HAQAST. There's this concern about increased ship idling off the coast due to the supply chain issues, and that led NASA to investigate on NO2 levels from the ships. And what you see here is both off of the coast of Los Angeles, and there's the port is down here, sort of the Long Beach and Los Angeles port activities are down just to the south of Los Angeles, to the west of Huntington Beach, and then also off of New York. And in both these images, what you see is the increased NOx when you compare the 2021 levels for a period during the fall with the levels in 2018 and 2019 over the same period. And you can see that there's some increased NOx off the coast. Now, what you also see is that there's some increased NOx in other locations as well. And so the question is this coming from ship idling or whatever? Now, an increasingly interesting, or also interesting question is you also see these decreases that can be due to COVID restrictions. They could be due to other controls, etc. But you also see some increases. So it's a very complex picture. And again, I'll make that the comment that by combining the satellite images with air quality modeling can help us identify not only the sources, but also allow us to disentangle the impacts of meteorology and look at the impacts on additional species. So one thing that we're doing as part of this is that LA is looking at the effects of specific control programs, because in particular, Los Angeles has had a very active program to reduce emissions due to port activities, diesel trucking, etc. And so by combining the two types of information, we can address that question. The main problem, of course, is looking hyper-local, getting the details down at that scale. And for that, we've fused our results with some hyper-local, essentially dispersion modelings. And what that can do is also increase the temporal information. The satellites come over us at specific times per day, at least now for the NO2, that's going to change. Whereas often the highest levels can be during the morning or even during the night when you won't have such information coming. So by combining the two sources. So the main thoughts is I'd say that we've been able to use the satellite data very well for helping to identify where the local sources might be, as well as the extent of the impact of those local sources. Again, looking at the airport, we see that the impact isn't just at the source itself and the nearby communities. We see a broader impact with the plume, and that I would also note there's increased power from integrating the satellite data with other measurements and models to really help characterize the source strengths and link it to other pollutants. So there you go. Thank you very much.
Thank you so much, Ted. Really excellent opening talk that sets the stage for the others that we'll hear about, and covered the interesting aspects and complexities of trying to use space-based instruments to get at very fine scale information in cities. So our next speaker will be Byeong-Uk Kim from Georgia Environmental Protection Division. Take it away.
All right, can you see my screen?
Yeah, looks good.
All right, well, good morning, everyone in a Central Time Zone or Pacific, and good afternoon for Eastern Time Zone folks. My name is Byeong Kim. I'm working for Georgia EPD. I wanted to share what we have been using satellite data for our sort of regular work at our agency, and I would like to also acknowledge my co-author here, Xiangye Jiang, who has been actually doing all the work in this presentation. What I'm hoping for out of this presentation is to share what we've been doing, but also hope to get some feedback or information that we are looking for, where to get those and when those are available and things like that. Let's see. All right, I want to share where we are in terms of air quality status, and then I want to show some of the work that we've been doing for identifying the causes of air pollution events that we've been experiencing, and then what we faced in terms of challenging parts, and then I want to also share our wish list about better use of the satellite data. So this is what we call the design value. This is a regulatory term that basically specifying where we are in regard to Clean Air Act standpoints. And as you can see, overall, we've been seeing the downward trends, and we are meeting the ozone standard now, and we're hoping for getting approval for the attainment designation request to the EPA this year. And this is annual PM2.5. As you can see also that it's showing downward trends so far, and we have a little bit of bump there that I will get back to that a little later in the PM slide. And then daily also we got down to less than 12 microgram per cubic meter. So overall in Georgia, we've been improving our air quality quite a lot, I would say, but still have a remaining challenge for the ozone, especially because it's really at the borderline of the meeting air quality standard. Now, because of that, we've been making efforts to investigate each pollution event or exceedance event that we call whenever the measured air quality or air pollution concentration is above the next level. And we have 2 to 3 business days to finish the initial report, and then at the end of the year that we get all the certified data and the official data sets and the additional information at the time that we can get to develop the final reports. And I highlight here some of the items that we got help from the satellite data or tools that's part of our reports. And we basically include these things and then analyze and coming with the story, what we thought that what caused the air pollution events at the time, especially for the initial reports. And then we have a plan to run CMAQ and CAMAX modeling with the source apportionment tool to explain more quantitatively where each event had an issue and who contributed the most and things like that. And this is integrated maps that we developed the tool with a Python to generate these plots. in the past that we had to deal with the multiple plots and a back and forth to come up with our story about or explanation about the events. But now that we have this tool that combining all this information into one plot, that we can easily see where things coming from and which potential major sources that the air mass has been passed through and things like that. And then we've been using NO2 column data quite a lot recently. And what we noticed, at least in our area, is that, like Ted mentioned, that in Atlanta Airport, we often see very bright color, or high VCD values around. Sometimes that's even higher than the power plant locations. And the other thing that we noticed is usually the day that we have extents, that it turned out the NO2 column values are higher than the day before and after, usually. It's not always that way, but I would say more than 90% of cases that we've been seeing, that's likely the case. And the other thing that we've been using was the true color image to identify the location of the fires. And even though we have a HMS fire data out of the aeronautics, but we wanted to see how the plumes are dispersed if possible. So these are kind of snapshot images that we inserted in our initial reports. And then we try to look at the wind patterns along with the NO2 column data with the interpolated ozone concentrations to see where ozone formed and moved and things like that. And we've been seeing two typical pattern in Atlanta recently, that it's very isolated. That's one characteristic. The other thing is when winds are blowing in enough speed, then you will see the most likely high ozone is happening around Atlanta core. And the other situation is where winds are very slow or calm situation, then it's likely we have a ozone extents event right at the center of Atlanta. So that's what we've been observing in the last, say, the 3 or 4 years. In the, I guess, of 10 years or before, in Atlanta area, when ozone extents happens, it's likely more likely the regional or city level events. But now we've been seeing it just hits 1 or 2 meters right on the spot. And then at the end, as a part of the final report, we usually try to see the monthly average or seasonal average of the NO2 column, see if whether that make kind of sense with what we initially assessed. And this one compared the tropomy data from 2019 through 2021, and you can see that obviously 2020 it had a little lower NO2 column data. And here's one of the caveat. I believe that the 2021 had algorithm changes happening by the time that we did this analysis. So the value in 2021 might be a little higher just because of that. The one thing that we've been trying to do is the regridding with the modeling grid that we would like to use in the future. So you can see more higher resolution picture here that we're going forward. Like Ted mentioned that eventually we would like to do the fused data visualization too. But for now, we've been switching over from here to regridded data that we've been processing by ourselves. The other thing that we've been trying to do, which will be likely used in this year for our initial report for the PM2.5, is to overlay the tropomy data with the fire location that we can get out of the HMS. And then we have a fire permit data we got from Georgia Forestry Commission. And this new plot, I think, will helpful for us to identify, like this one, large fires that happen nearby. So if these fires can be identified in the path of the, say, high split trajectory to the exceeding mountain, I think that will be very useful information to explain the cause of the events. The other thing, it's a kind of new that I don't have a picture for the Atlanta area, but I got this from one of the slide deck, the links that I think she's working for NASA. But anyway, the ghost satellite that had a true color picture that helped to identify the evolution of the plume movement. So we would like to get these high resolution data for Atlanta area. And she is kind enough to offer to work on Atlanta archived data for certain days that I shared with her. Now, challenging part is we have to pull this data pretty much manually now on multiple sources. We come up with some script to do a little bit of automatic downloading, but yet it involves many manual steps. And also we had to create our custom tool, like a Python script to combine these informations or data sets. And also some of the data that we try to use are limited in time, like once or twice a day. And I tried to look at the L1 product for certain items before this talk, and it's been a little challenging to handle. Although now the other product, like goods products, that I can get some help who is expert in that data product, that's a good thing. But in general, I think the spatial resolution and temporal resolution that we are looking for often requires L1 data processing. And also the regrading is often needed. So this is our wish list for better use of the satellite data going forward. We would like to have an hourly true color image for the past days. And this one, I think, again, I get a help from CIRA. I guess I have to correct that the Lindsay is actually working for here, not for NASA. Let me correct that. And there is the web application called the Slider. So we can use Slider for our initial reports, but the data archived, I think archived data are not necessarily available for the area that we are interested in for the days that we had the instance, if we want to do it in a final report. But going forward, I think the Slider-like app will be very helpful for us to save those imageries along the way. And we would like to have a 1 kilometer hourly. I think the tempo product will be very helpful for this one. But in general, we wanted to have a higher resolution in space and time for these products. And also, it would be helpful if we can get the satellite data product published in on the same grid that we've been using or will use going forward for our regulatory modeling, like a US CONUS 12 grid, or what we plan to use as a super high resolution grid, like a Georgia 1.3 kilometer grid. And also, I would like to know and hope for the tools that's similar to like RSIG 3D that the EPA have been published on their website and through the standalone application, which help us to visualize, analyze data with the on-demand downloading and the user-defined area and time. The other thing is, if there is any tool to do those overlaying efforts that we are making with our custom tools and things like that, if we can get those kind of on the fly at the like a server level, and we just can download the data that we want or analysis product that we can download, then I think that will be extremely helpful, which also we are hoping to include like a online version of the high-split run in the background, so that we don't have to run it at our end by downloading those data and then run the script. All right, that's all. Thank you.
Thank you so much, Byeong. Really excellent presentation that dovetailed so nicely from Ted's. And I have to say, I really appreciate the specificity of your slides on the challenges and wish list. That is extremely helpful to have for this community to hear about. So thank you so much. And we will now turn it over to Abbey Nastan from NASA Jet Propulsion Laboratory.
Great, thank you. And let me get my screen share started here. So hi, my name is Abbey Nastan, and I am the Deputy Program Applications Lead for the Maya project. So Ted alluded to Maya a little bit earlier in his slides, and you might have also heard it mentioned yesterday morning in John Haynes' overview talk. So it's been a couple of years since I presented at HAQAST, so I wanted to give a general overview as well as some updates, and also talk about a few special events that we have going on at the moment. So can everyone see the slides?
Yes, it looks great.
Perfect, thank you. Okay, so I've gotten rid of my usual slide that I keep at the beginning of most presentations, talking about how PM is the top environmental risk factor to human health. I think all of us in this meeting understand that. However, in order for air quality managers and governments to make effective decisions about how to best protect human health, it's important to understand which types, as in which chemical compositions, which mixtures of PM increase the risks of which diseases. And this is a question that Maya was selected in order to investigate. So like TEMPO, Maya is a NASA Earth Venture instrument. We're in the same program. We were selected in March 2016, so we are a couple of years behind TEMPO in terms of development. And as you can see on this slide, our science objectives are to connect the various types of particulate matter air pollution with specific health outcomes. So on the right side of the slide, I want to draw your attention to, if you have seen previous presentations about Maya, you might have seen a launch date of 2022. We are having a bit of a launch delay, and we're expecting launch circa 2024, with hopefully more concrete information coming for you in a bit here. Once we do launch, we're expecting a mission length of approximately 3 years with a possibility for extension. The instrument type of Maya is an imaging spectropolarimeter. And it's important to note that Maya is a targeted project. We will not be able to observe the whole globe due to our observing strategy. And we have specific target areas, and I'll show a map of those a little bit later on in this presentation. Okay, so this slide is basically the work of hundreds of people for many years compressed into a single slide. I don't have time to go into a huge amount of detail about any of this, but if you have questions, please do ask. So the satellite instrument, as I mentioned, will be an imaging spectropolarimeter, which basically means it'll be a camera with 14 spectral bands, 3 of which will be able to collect polarimetric information. We'll combine the information from the satellite instrument with data from surface PM monitors and with chemical transport modeling in order to produce our PM data products. Then epidemiologists on our science team will use health records to conduct the health studies that will fulfill our science objectives. Okay, so I wanted to show you a few pictures of the instrument progress. So the camera, the heart of the Maya instrument, has been assembled, and you can see a picture of it here on the left-hand side of the slide, so that's very exciting. In the middle here, you're seeing an actual image taken by the Maya camera. So we've combined the red, green, and blue spectral bands in order to give you an approximately true color image. You'll notice it's a little bit out of focus. That's because Maya, being a satellite instrument, is focused at infinity. And of course, this sign that we took the image of was only a couple of feet away from the instrument. So that's why it's out of focus. On the right-hand side here, you'll see an image of our gimbal assembly. So the next major step of the Maya build is to integrate the camera into the gimbal assembly. So we're looking forward to that. So here, as promised, is our target map. I know it's a little bit small on this screen. Please know that you can check the target map at any time by going to our website. So the primary target areas that are shown in blue on this map are the areas in which epidemiologists on our science team will be doing health studies. We're required by NASA to have at least 10 of them. There are currently 11 on the list. And they have been selected to optimize for health studies, and you can see those criteria on the left-hand side. You'll also see on this map that there are a large number of green target areas. Those are our secondary target areas. They have been selected with input from the community, including from Maya early adopters. And the objective of the secondary target areas is to provide data of interest to the community. Now, at this point, we can't say for sure whether we'll be able to produce the full suite of data products in the secondary target areas. That's going to be constrained by compute power and also by the human effort that it takes to, to identify, to collect, to collate, to quality control, all of those things, the surface monitor data in each of the target areas that we want to produce PM data for. But we will have Maya observations for these areas, even if we can't produce the full suite of data products. So it's important to note each of these target areas is identified by a primary city of interest, but please note that each target area is roughly the size of the state of Florida. So it's quite a large chunk of real estate and often includes both urban and rural areas. Okay, so just to give you a very quick drive-by tour of the Maya data products that you can expect. So NASA categorizes data products from Earth observing instruments according to level, and as the level increases, basically you're getting more processed. So we start with level 0, that's the raw data coming down from the satellite. This isn't really of use to anyone in its form because it is just raw ones and zeros, and therefore it won't be a public data product. We then process that into level 1 data, and since Maya is at its heart basically a camera, the level 1 data you can think of as pictures. This will be mapped at 250 meters. The example data that I'm showing here is from our airborne prototype Air MISB. So that's at a slightly higher resolution because of course these images were taken from a plane rather than from a satellite. Then we'll process that data into level 2 aerosol data. So that'll include all of the typical things you're used to seeing from a satellite aerosol product: aerosol optical depth, single scattering albedo. We'll have size, shape, and absorption information, all of that stuff. And that'll be mapped at 1 kilometer resolution within the target areas. Then here are the PM data products, which I would assume would be of the most interest to the people in the room today. We have 2 different versions of our PM data. The difference between them is that that level 4 product that you see on the right is gap filled to account for clouds, shallow water, any of those things. And we'll also be using our bias corrected chemical transport model to create predictions of PM even on days without Maya overpass. So that's the difference between those 2 products, but they will both be created at 1 kilometer mapped resolution in the target areas, and they will both include those concentrations of those variables that you see on this slide. And all of these products will be in NetCDF format, and all of them will be available free of charge from the Atmospheric Science Data Center. Okay, so I know that we have some members of the Maya Early Adopters program in the room today. It's great to see you. If you are not currently an early adopter, I'd like to invite you to join. We welcome anyone who has a potential interest in using Maya data down the line. We really want to receive your feedback on our plans for Maya data products and our target areas so that we can make sure that the Maya data is of most use to the greatest number of people. From your perspective, the Maya Early Adopters program gives you a chance to offer feedback, gives you access to test data products, which I'll mention in a minute, and also gives you the chance to collaborate with the science team, with myself, on any questions that you might have in order to get started using Maya data. Okay, so I mentioned special events, so that's what I want to cover next. So we do have a special event going on right now. Myself and Aaron Nager, who I see is in the room, who's the DPA for Tempo, we have organized this crowdsourcing challenge in collaboration with NASA at Work and Driven Data. So it's called the NASA Airathon, and the premise of it is that participants submit algorithms that they design to predict either PM 2.5 or NO2, or you can do both, of course, in certain geographic areas using at least 1 satellite data source, though you can use as many other data inputs as you would like. And these algorithms will be ranked according to R-squared performance against reference grade ground monitor data. And the top performing algorithms will receive cash prizes. So this challenge just opened earlier this week, so we're very excited about that. We hope that some of you in the room today may be interested in participating. The challenge is open for submissions until March 21st, and I've included the links here to get more information about that. And just one other thing to mention before I wrap up here is that we've recently released our first version of the Maya simulated data. So this is test data, not intended for scientific use, just intended to help you prepare to use real Maya data. It's currently available through NASA Box, and I'll include a link on the last slide of how to get it. And then over the next year, we will be working to get it into NASA Earth data, similar to the way the tempo synthetic data is available right now. And then, of course, after launch, you will obtain the quote unquote real Maya data products from the same source. So with that, I'll wrap up. I'll leave the slide up with some helpful links. Please feel free to email me if you'd like to join my early adopters or if you have any questions. And here again are the links for the crowdsourcing challenge and how to receive the Maya simulated data. So great, thank you so much.
Fantastic. Thank you, Abby. Really nice presentation and so awesome to see the progress being made. Really great update. I wanted to remind everyone to put your questions in the Q&A. It looks like we had one from Scott Van Pelt that maybe was incomplete. So Scott, I don't know if you want to try that again in the Q&A, and we'll get to those at the end of all of the presentations. And now I will hand it over to our final presenter, who is Jay Baker from the Western States Air Resources Council. Jay, the floor is yours.
Great, thank you. Let me just share my screen here. Okay, hopefully everybody can see that. I feel like I'm gonna, first of all,
Okay,
thank
sorry,
you.
we can see it, but it's not in slideshow mode yet. I don't know if there's a delay.
Hang on, let's try this again. How about that?
Yep, that looks great. Thank you.
Okay, great. Anyway, thank you for inviting me to present. I feel like this is going to be a huge gear shift from the other presentations. We're going to go from looking at urban areas to wilderness areas, and we're going to shift also from looking at health impacts to an aesthetic standard in my presentation. So hopefully the gear shift is okay with everybody. I'm going to start by just talking a little bit about who WestAR and RAP are, and then I'm going to talk a little bit about the regional haze program. That's the aesthetics part of this, and then just some of the challenges that we have in the West when it comes to regional haze. So first of all, WestAR and RAP, we're a Western States multi-jurisdictional organization, formed several decades ago to basically as a way to help states to exchange ideas and share, help each other out with issues and challenges surrounding air quality. RAP, who's part of WestAR, tends to be the technical arm of things. But anyway, so we've been around for a while. One of the programs that we work in quite a bit, especially RAP, is called Regional Haze. And if you're not familiar with this program, like I said, it's an aesthetic one. It's in the Clean Air Act, where Congress says that they want to improve visibility or the vistas in certain natural areas, national parks and wilderness areas. You can see a few examples here: Yellowstone in the top left, and then going clockwise, Canyonlands National Park, Haleakala National Park in Hawaii, and the Jarbuch Wilderness Area in Nevada. So improving the visibility specifically for man-made pollution, or from man-made pollution, and reducing that is the goal of regional haze. And that's measured in several ways, but mostly we look at monitors. There's a monitoring network throughout the United States, and here you can see mostly focused on the Western United States. This is the Improved Monitoring Network, and these monitors operate and give us data every 3 days, and it's over a 24-hour average period, and they speciate the data by different types of particulates. So Maya sort of piqued my interest, even though we're talking very rural areas here. But looking at ammonium sulfate and ammonium nitrate, and looking at coarse mass and organic mass and so forth. So one of the issues that we'll talk about is understanding what visibility looks like over the terrain of any of these Class 1 areas. So here you see on the right Yellowstone National Park with that purple pin right in almost in the center of it. That monitor measures the visibility for Yellowstone, but it's also used for the surrounding area, for just to the south Teton Wilderness Area, and further south to Grand Teton National Park. And then that green Class 1 area to the west on the left side is Red Rock Wilderness Area as well. So that one monitor covers a wide area with a lot of different topography and different weather patterns even. And so it's really difficult to get a picture of what's happening in these areas. Now, also, when we're measuring visibility, the focus of the recent regional haze program, like I said, is man-made air pollution. And so in the first sort of round of planning for improving these vistas, the focus was on the very worst days. So we'd look at the monitoring data and say which days were absolutely the worst, the 20% worst days out of the year, and how can we improve those, and then make sure also that those clearest days didn't get any worse. The focus was changed from that for the second round of planning, which started just last year in 2021, to look at what we call the most impaired days. And the idea was to pull out some of this pollution that was not man-made, like smoke or dust, that's not really controllable. Smoke from, I should say, specifically from wildfires. So here on this map, you can see again the Yellowstone area with the monitor, and I'll just point out a couple of things to keep your eyes on. First, the tan blobs are smoke data from the AirNow database, which I believe is satellite-based images of the smoke plumes. Then also notice the dates up at the top left, and then the deciviews, which is a measure of visibility, in the top right. So on this day, August 25th, 2019, visibility was 10.35 deciviews, and that's not great. The lower the deciviews, the better the visibility. This represents about 85 or so miles of clear view in Yellowstone. And you can see there was some smoke in the area, but again, hard to say exactly how much. But this was just one of the days with not good visibility. Oh, the other thing I want you to pay attention as we go through, I'm just going to go through a few maps, same maps, looking at the visibility on that day and the smoke on that day. I'll identify which of those are most impaired, in other words, impaired by man-made pollution versus something like wildfire smoke. And so in theory, you should see smoke like this day on August 28th. And that's not a most impaired day because it was probably the visibility was made worse by the smoke itself and not something that we could control. However, on this one, you'll notice 3 days later that the visibility improved, even though lots of smoke moved in. We're at 7.12 deciviews. On this day, the smoke again has moved out. You can see little bits and pieces here and there, but the visibility actually decreased slight, not by a lot, but a little bit. Now we get to September 3rd, another 3 days later. This is a most impaired day. However, you see a smoke plume going starting right in Yellowstone. And the visibility is about where it was on that first day that we looked at. So we would expect this to not be a most impaired day if it was the smoke from that fire. But you also notice that the smoke may or may not be impacting some of the areas that are using this monitor to measure visibility. Again, 3 days later, this is also a most impaired day. There's a little bit more smoke, but it seems to have cleared out of the actual national parks and wilderness areas. And visibility is better, down to 7.5 deciviews. September 9th, another most impaired day, so 3 in a row. And again, smoke tends to be cleared out. So those last two are probably what we would assume would be logical for most impaired days. And then the final one, Another 3 days later, each of these are just 3 days after the other. The visibility is at 2.93. So now we've gone from about 80 miles of visible range to 180 miles of visible range. Another way to look at that, this is the monitoring data itself, and this is the whole year. So I'll zoom in on just those days that we were looking at. And we see from the monitors and the species that those 3 that are outlined in blue were our most impaired days, and the others were not. And you can see there are similarities even between those days that are classified as most impaired and those days that we sort of weeded out statistically. So that's one of the issues, is trying to characterize the visibility over the area rather than at a single point, which Ted made a good point with that in his presentation earlier in this session. The other issue that is knowing where the pollution is coming from, where the emissions are coming from. And we do emissions inventories. We use modeling to model where the emissions are coming from, but there are gaps in that, and I just want to outline a couple of those gaps. So first of all, you see here, now we're in southern Utah, northern Arizona. Those orange building-like structures are coal-fired power plants. So those are really easy to identify, right? Point sources, we know where they are, we know how much they emit, we can model where the pollution goes and say this is how much of an impact they have on our class 1 areas. On the other hand, you see all of the yellow and the green federal lands that are multi-use lands. So it could be used for grazing, or in the case you see Arches National Park and Canyonlands National Park, hopefully in this map. If you've heard of those, or if you've heard of Moab, Utah, it's an enormous recreation area. Millions of people come there every year to recreate, and they don't just go to Arches and Canyonlands. They do that, but they're also on all of those lands that are yellow, and some that are white even, but and the green ones, and they're recreating out there with OHVs, off-highway vehicles, or they're camping and having fires. And not trying to say that any of those are bad, but those are emissions that are difficult to count in a traditional emissions inventory or even in modeling. Another source that's usually a little bit more well-known, on-road sources. I'm illustrating some of that here with this map. Happens with visitation, and it's not, well, again, looking at it on a local scale, like we're doing here. Oh, I see I'm running low on time. But it's difficult to quantify right in these areas that we're looking at. So for example, you see this map where there's visitation numbers represented by the size of the icon. And like I said, we're looking in Grand Canyon National Park, 3 to 6 million visitors per year. Same in Zion National Park and so forth. And this causes and other impacts. We don't want to deter people from coming and enjoying these incredible places, but we also want to understand some of the impacts that come from those. And again, the picture here is an illustration of cars idling, waiting to get into the south rim of the Grand Canyon. Just waiting to get in has even an impact as you sit there and idle. So again, these are the issues that we hope that we can help, or at least have some help using satellite data to resolve the emission sources and also characterize visibility over a broad area. So with that, I'll finish up and open it to conversation. If you'd like to contact me for additional conversation, my contact is on this slide. But I think we'll go to questions if I'm correct.
Thanks so much, Jay. Really great presentation. My camera, of course, just stopped working again. I apologize for that. It's been doing that for the past couple of days. But hopefully you can still hear me. Yes. And what I'd like to do is we have some questions coming in both to the Q&A and the chat. A lot of these are specific questions about Maya for Abbey, and I'm going to get to them first, I want to start with a question from myself, maybe to Ted and Byeong and Jay, if you'd like to answer as well. And then I'll give Abbey some rapid fire specific questions about Maya. So I wanted to just ask you, we heard some questions earlier today and yesterday about new emission sources, like, warehousing or port activity or data centers, things that are sort of popping up and changing the spatial structure of where emissions are occurring. And I'm wondering, you've all talked about using both satellite data as well as ground monitoring, and also Ted and Byeong, you talked about chemical transport modeling. How can we use these different data sources together to try to identify these emerging sources of pollution as they occur, sort of to give more real-time information to the public and decision makers?
So I can start with that. First, I'll say that with the current technologies, Tropomi has really pushed the bar quite a ways, but it hasn't pushed it all the way that we want. So it can't be a moderate-sized source that we're going to start identifying. Right now, so we can really see and characterize some of the larger sources, et cetera. So that we can do, at least for NO2. For PM, actually, with finer scale resolution products, we can go deeper. But I think actually the next generation, we're going to be able to push that much further. So what I think we can do now, and that's really we can characterize, are these larger sources that we know are there, but maybe don't have a full appreciation of their extent of their impact. And that, I think, is something that the satellite results are really able to provide us, both positively as well as in terms of the extent of their impact, but also how they've changed some of the details over time that we weren't able to do before. And I would take specifically the port area activities around Los Angeles, where they've done these extra controls that I think this is an area where the satellite imagery combined with the air quality models can really come into play. And I think the modeling is important because, and I think Dan pointed this out yesterday, if not others, we still have all these other confounders, if you will, the meteorology, but also the other sources that are there. So I look at that as that what it's really their power is looking at the extent that we can simulate with air quality models, but we don't, it's still a model, whereas this is real live data that we can use. So I hope that starts to address your question. Maybe I wandered a bit much, but.
Thank you, Ted. Some great insights there. Byeong or Jay, do you have any thoughts?
I think it's kind of along the line with what Ted just shared in terms of identifying some of the potential sources that's not captured in the inventory. So in traditional stationary sources, that I would think that many people attempted to compare like a top down versus bottom up, like a bottom up meaning the inventory that you probably know where they are, that you would think. And then in the top-down approach, based on the satellite, that you can see some of the high NOx area where the inventory didn't say there is anything identified already. I think one of the slides that I shared for the fire is a little off from that where we didn't know where actually the sources are. The permits is a permit in our case that doesn't really guarantee that that's actually happening at the day. So I think that's from our point of view, that's the whole reason that we wanted to utilize satellite imagery and start seeing whether that is really correlated well with what's been known with the given information. I guess the other side is, I guess the modeling parts is also kind of go along with inventory I guess, the topic that I just talked about, because the modeling is obviously based on the top-down bottom-up inventory, but at the same time, there has been, I think there has been efforts to do some sort of the data fusion based on the ground monitoring, kind of doing also blended with the inverse modeling. And all those things, I think, along with the satellite data, will be helpful to potentially identify those, kind of unidentified sources. I hope that this effort is expanded to, like Ted said, that expand to the PM2.5 and eventually large VOC sources once we start tapping in the high resolution the formaldehyde data sets. So I will stop there.
Thanks, Byeong. Yeah, it certainly seems like we're sort of on the cusp of some exciting new techniques to use some complex but very helpful merges, integration of different data sets, and yet there's still a lot of uncertainty, especially as we just heard in the last session about communication, how difficult it is to communicate to local residents or decision makers when some data sets disagree about where emissions might be. Let me just see if Jay has any thoughts to add here. Otherwise, we can move on.
I think I'm good. They both Ted and Byeong said pretty much what I was going to say about combining sources or resources, satellite versus with modeling and monitoring and so forth.
Okay, great. And Abby, I promised I would give you some rapid fire questions. I didn't mean to exclude you from answering the last question either, if you have any thoughts there.
I think we can move on to the other questions.
Right, so there's a lot of, I detect a lot of excitement about Maya, which is really great to see. And some specific questions. First of all, one that you had answered, but just want to ask it orally as well. Can you specify the temporal nature of Maya measurements?
Right, yeah. So Maya will be placed onto a polar orbiting satellite. So unlike TEMPO, it's not going to be geostationary. So unfortunately, we won't get multiple observations per day, but we will be able to observe targets around the globe. So the temporal nature of the Maya data products is that the level 4 PM product will be produced every day for each of the target areas in which we are producing it. So at least the primary target areas, maybe the secondary target areas. And that product will be daily averaged, important note. The rest of the data products will be produced on days that Maya overpasses that particular target area. So for primary target areas, we'll be observing them at least 3 times per week. Secondary target areas, we don't have any specific requirements, but we're aiming for at least 2 times per week for the secondary target areas. So the rest of those data products you'll get on those days. And it's important to note that it's not a set pattern, so you'll get kind of random days of the week. So hopefully that answers your question. Thanks,
Abby. The next question is about the target areas. So we have a few that I'll merge into one question here. Are Maya dataset products available globally or only around areas near the primary target areas? And a follow-up question to that would be, will the same level of detail, I think you mentioned that there's going to be a area, I think you said around the size of Florida, around each target city. Will the same level of detail and information be available for that entire area, or is there something special about the urban area itself?
Right, yeah, great questions. We're only referring to it by the primary city for reasons of convenience. It's a lot easier to say, the Los Angeles target area than it is to say, southwestern US comprising parts of California and Nevada. So, each target area does have a bounding box that has an area approximately equal to the size of Florida. And within that bounding box, we will be producing the Maya data products. So the answer to the first question is, unfortunately, no, we will not be producing data products outside of the Maya target areas. The reason why we have these target areas is because you saw a picture of the Maya gimbal assembly. So the Maya camera will actually be scanning back and forth across each target area multiple times per overpass to collect measurements from multiple angles. That's part of the Maya observation strategy. And because of that, because of the maneuvering that we have to do with the camera, we can't necessarily be looking at areas outside of the target area bounding box. And the other reason is, of course, because we need that surface monitor data in order to create PM products. And unfortunately, it's just, it's an effort too large to be able to do that exercise of identifying and collecting surface monitor data for the entire globe. That would be a huge effort. So that's the reason why Maya is a targeted investigation. So basically each target area is approximately the size of the state of Florida, and the primary city might not necessarily be in the exact center of it. We've kind of optimized the location of the bounding box in order to get the maximum possible population or items of interest within the box.
Great, thanks. And quick follow-up and last rapid fire question for now, and then there's a question for Jay that I want to ask. How can somebody find out if they have an area of interest? How can somebody find out if they're in that bounding box? And is there any way for folks to suggest new areas of observation?
Great. So we are working on a tool that we will be able to share with the public that will have, the full bounding box information. Unfortunately, that's still in work, so I can't share it with people yet. But if you have a question about, I seem to be close to one of the target areas, but I'm not sure whether I'm in the box, just send me an email and I'll be happy to send you a screenshot of that particular bounding box. And the question about, are we open to adding new target areas? We are kind of at this point approaching the maximum number of target areas that we can kind of handle for Maya, but I'm not going to say don't ask. Please always ask, and we'll think about it and see what we can do. So if you have a request for a new target area, please just send me an email. We'll discuss it among the science team and see whether it's possible or not.
Thanks, Abby. Really appreciate your willingness to talk on all those topics. So thank you very much. Jay, there's a question for you. Really cool talk, which I agree with. Are you sourcing the data for the regional haze rule or other rule? I'm wondering how rules are structured that ignore smoke, or is this an attribution exercise?
This is more, I guess, an attribution exercise, but the rule. It is kind of curious. The rule, at least for regional haze, doesn't say specifically exclude smoke. It just says, look at anthropogenic sources, and those are part of the most impaired days. EPA's guidance then suggests sort of a statistical method for excluding those days, which is, in its simplest form, is basically saying, let's pull outlier data out, and outliers basically those that are over a certain threshold, especially when it comes to the pollutants that cause smoke or dust, so organic mass or coarse mass. And as you saw, it doesn't always work, but ultimately the rule doesn't specify, so that means it really is in some ways up to the states to identify the best way for pulling some of those sources out.
Great, thank you. I want to get back to Ted and Byeong. You both showed a lot of uses for NO2 data in identifying local sources. And I wondered if you could comment on the current limitation of the once per day flyover time in the mid-afternoon, in terms of the potential consequences that might have for understanding the magnitude of the contributions from different sources. So traffic versus the airport versus wildfires versus the power plants, for example. And what are you excited for tempo? I guess probably the answer to that is yes, but what are you most excited for tempo in terms of filling?
Well, I'd say most excited for tempo is as much the spatial resolution. I do say that the temporal, missing some of the temporal information for NO2 is a limitation now, in that, as I noted, traffic and many of these sources, their major impacts are not at the time of the flyover. Just if you start looking at the meteorology and the source strengths, you know, that they happen at other times. I think we can do a reasonably good job using models and ground level measurements to make up for that temporality miss for many of the major sources. Just, you know, we know what the temporal distribution of emissions are from power plants because you've got measurements, and we have quite a bit of monitoring for like traffic, et cetera, to come up with that. So I'm excited about, you know, I think really for tempo, it's some of the spatial information, but also the information on other pollutants, formaldehyde and such, I think is going to be tremendous as well. That we're still missing. You know, that Tropomi has not been as successful with formaldehyde retrievals, and that's, you know, if we start looking at some of these other air toxics, I think that's going to be important. So while I think there is we are missing something on the temporality from current Tropomi and other products, we can do a reasonable job of making up for that with models and other measurements. You know, that's not to say it wouldn't help us identify some other sources, but it would, you know, in terms of identifying really where the peak is and when. So Byeong.
In general, I agree with you that higher spatial resolution will be definitely helpful. The temporal aspect of it, I'm really excited about it, particularly because the initial report that we've been developing along the way, my observation is there is some correlation definitely with the traffic condition in each specific day that affects the diurnal profile of the NOx emissions in that day with the potential ozone exceedance at the specific monitors. And right now, like I said, that for the long-term average condition, the model will do a reasonable job, but very specific day, part of it is we likely have a less exceeding day going forward. So it's going to be getting harder to have more samples to analyze. That's kind of controversial parts of it. So because of that, I think the higher resolution data in time will be definitely helpful for us to have a good correlation analysis between the traffic condition and the NOx emissions, especially from on-road mobile sources. So I'm in terms of my excitement about the tempo, that I'm very, very excited now. I'm really looking forward to utilizing those data sets once they are available.
And I agree with that. And I love to hear the excitement for both tempo and Maya coming up. And so final question back to you, Abbey, about Maya is, you noted a slight delay, and sometimes that can actually present opportunities. And there's a question here about opportunities that might present for using some suborbital measurements for evaluation and other things. I'm wondering if you can reflect on that and any other, you know, opportunities that you can think of that might have come from having a few more years here.
Right, yeah, that's a great point, is that even though it's unfortunate that we're experiencing a launch delay, it does sometimes present additional opportunities. Yeah, so Amber, I hope we can talk soon about possible synergies between Maya and AOS suborbital campaigns. That would definitely be very cool if we could organize something there. We are expecting to be able to observe targets of opportunity for Maya. Those obviously weren't on our target map because they would be short-term and ad hoc, but it is a capability that we expect to have. We're expecting to be able to do our observation planning about a week to 2 weeks ahead of time. So that gives you an idea of on what time scale we can add more observation targets to the target plan. Yeah, there may be additional opportunities, perhaps say to create enhanced simulated data that can provide people some good resources while we're waiting for Maya data. Unfortunately, you know, the launch delay is relatively recent. We've only had the news about it for a couple of months now. So we're still kind of sorting out how everything's going to work budget-wise and timeline-wise and team-wise. So basically, please hold that thought, and we hope to have a better idea soon.
We'll check back in at the next HAQAST meeting. Okay, any final thoughts from any of our panelists? Otherwise, we'll hand it over to Jenny for some closing comments.